So today we discuss about the risk neutral measure in terms of continuous case. As you remember in FFM when we discussed the discrete case, we had two probability measure functions, right? First one is the actual probability of coin toss. So what's the probability of getting a head or tail when we toss a coin randomly? Okay, and that one was denoted by P. Okay, um, denoted by P. Sorry. Uh, Okay, so two probability functions. The first one was denoted by P. Okay, this is the actual probability. Then we were calculating B0, the premium, and then in the process we got two terms, P tilde and Q tilde. Okay, and then we saw that the P tilde plus Q tilde is equals to 1. The P tilde Q tilde was found in terms of U, D, and R, and then we calculate the P tilde plus Q tilde, we got it equals to 1. So we can assume that there was P first, and then we have another P tilde probability measure function, so that the p tilde of h is equals to small p tilde and p tilde of t is small q tilde, so that this one is something like another probability function. Okay, and we name it the risk neutral probability measure function. Okay, so then we had two probability measure functions. One is p, one is p tilde. So after that, we need a relationship between them. So we define Radan-Nikodym derivative z. So that z, sorry. So that z of omega is equals to p tilde omega divided by p omega. Okay. So once we have defined this z, then this one is the relation, the p tilde and p, this is the relation, and then we also found that the expectation of z is equals to 1. Okay, we proved all this thing. Once we have done this, next stage was the derivative process. So Radan-Nikodym derivative process we defined by zn. The zn is actually expectation, so it means, so it's something like expectation of the z given the information received at time n. Okay, this one was the case for the discrete time. Now we are defining the same thing for the continuous case. Okay, the risk neutral measure. So how we do it? We begin with a probability space omega fp. So this is the actual probability. We start with this one, and the non-negative random variable z satisfying ez equals to 1. The expectation with respect to p of z is equals to 1. We then define a new probability measure p tilde by the formula p tilde of any event a is integration over a z omega dp omega. So any random variable x now has two expectation, one with respect to the p, one, another one with respect to the p tilde. Okay, so we denote them by expectation of x, ex, and e tilde x. Then the relation between these two type of expectation is this one. Okay, the e tilde x is exj. This is the relation. So you also have expectation of x is e tilde x over z in case probability of z is greater than 0 is equals to 1. Okay, so cannot be the z, the probability of z greater than the probability of z is equals to 0. Okay, so then in that case, so write in terms of expectation of x is e tilde of x over z. We now say the z is the Radan-Nikodym derivative of p tilde with respect to p, and we have this relation. Okay, this relation is almost similar as we had in the discrete case. Okay, so if you remember how we define the Zn is E and Z, right? The Zn is E and Z. This one. Okay, this is the thing. So we also have E and Z is Ez given Fn. Okay, it's you can say it's a equivalent thing. Huh? E and Z and Ez given Fn is a equivalent thing. So same way we can continuous case we can define Z of t is E of Z given Ft. Okay, we proved that this Zn was a martingale. Now in the continuous case also we proved that this is a martingale, the Zt. Okay, so what we consider S is less than T. We consider the S is less than T. Okay, so E of ZTFS, we can use the iterated expectation, conditional expectation. So we are trying to find the prediction of Z given the information T, and then we try to predict that this thing given the information Fs. So using the iterated expectation, we can write this is equals to expectation Z given Fs. Okay, so this one is actually same as Zs. Okay, if you follow the definition here, if you follow this definition, the Zt is equals to E of Z given Ft. So same thing here is Zs is the expectation of Z given Fs. Okay, so we have expectation ZFS is equals to Zs. That means this is a martingale. Okay, next one is so as you see here, the first we have three things, right? Last time also we have three things. So first one is here. The expectation tilde x is equals to E of xz. This is true for any random variable x. Now we consider some random variable which is known completely at time t. Okay, y is an ft measurable. Y is an ft measurable random variable. Okay, so in that case the sorry in that case the e tilde of y in that case the e tilde of y will be e of yzt. Okay, the proof is exactly similar like in discrete case. So we start with e tilde of y, then it is e of yz for any y, this formula valid. Now y is ft measurable. Okay, so it's known at time t. So we write iterated conditional expectation e of yz given ft. So you can write down y is known, so y comes out here. Okay, y comes out here. So e of y expectation zft is zt. So it's e of y zt. Okay, there is another one similar to last time is the conditional expectation e tilde. Okay, e tilde y given fs is equals to 1 over zs e y zt given fs. Okay, we will skip the proof of this one like last time also we skip the proof. Okay, okay. So next thing we discuss today is the Girsanov theorem. Okay, what does this theorem state is very simple. It states that suppose there is already a p, huh? There is already a p probability distribution, and then wt is a Brownian motion with respect to this p. Then now if we have another probability distribution p tilde, another probability measure function, sorry, p tilde, then we can have a new Brownian motion w tilde t if we can write this in terms of wt plus integration 0 to t theta u du. Okay, if we can write in this form, then the w tilde t is also a Brownian motion with respect to p tilde, with respect to the risk neutral measure. Okay, this one is equivalent to this form. So if you consider the derivative, so dw tilde t is equals to dwt plus, so this is theta t dt. Okay, maybe this one is easier. Okay, it's easier than the w tilde t. So so whenever we can find some dw tilde t, follow this formula, follow this what do you say is like we have another wt which is given as a Brownian motion. So if this one can be written as dwt plus some adaptive stochastic process multiplied by dt, then we say this is a new Brownian motion with respect to the risk neutral measure. Okay, we apply this one in the next theorem, in the next result. So now we consider that there is interest rate RT. Okay, so far we always discuss the interest rate is fixed, is a constant, R is fixed. Okay, last time. Now we consider the interest rate is RT in here. Okay, so last time when we talk about when we talked about the discounted process, discounted stock price, we always consider e to the power minus rt, right? We always consider e to the power minus rt st, or maybe e to the power minus rt xt. Okay, discounted, this is discounted. Okay, now we have the interest rate is RT. So the discounted process means we have to multiply by this new process dt. Okay, how to define dt is it is e to the power minus integration 0 to t. We cannot write RT anymore, right? It is t here, so it is integration minus e to the power minus integration 0 to t rs ds. So if rs equals to RT, if rs, yeah, sorry. So if rs equals to r, this one integration e to the power minus integration 0 to t rs ds will be e to the power minus integration 0 to t. So this is r ds, so it is e to the power minus rt. Okay, so same thing here. Okay, so now consider the DST. DST. Okay, maybe this alpha last time I think we followed mu t. Okay, so same thing. It's just we changed the notation here. So this one is mu TST dt last time. Now we write alpha TST, but it's same thing. So DST is alpha TST dt plus sigma TST dWt. Okay, so we have to find d dt st. D dt st means what we have is d dt. So this is d dt multiplied by st, and then we have dst multiplied by dt, right? We have you understand, right? It's d, so dt dst plus st d dt. Okay, so we must find out the d dt first. D dt. We find the d dt here. How to find the ddt? Suppose this one is e to the power minus integration 0 to t rs ds, right? So you can consider this is like the dt is actually something like e to the power minus maybe I write it here again. Okay, so we write e to the power minus, sorry, so e to the power minus maybe I write xt, e to the power minus maybe xt is better, e to the power a minus xt. Okay, so that when we need the ddt, when we need the ddt here, we can write down this is actually equals to, this is actually equals to del f del del f del x del x dxt and plus half del 2f del x2 dxt dxt. Okay, so now what is xt? This one we can also take plus, same thing. Okay, anyway, so what we have here is xt is equals to, maybe it is just right, e to the power xt. Okay, no need to take plus. So xt is equals to minus integration 0 to t rs ds. So what will be dxt? Dxt will be minus rt dt. Okay, so when we have this dxt, dxt is already here. Dxt is minus rt dt. When you have this dxt dxt, if you multiply dxt dxt, you get a dt dt, which will be 0. Okay, so this one will be 0. So this one the dxt is actually dt. So this will be 0. So you only have del f del x dxt. Okay, so del f del x will be how much? F is e to the power xt, right? I write here. So f xt is e to the power xt. So if we have del f del xt, it will be e to the power xt. Okay, or e to the power x, I mean e to the power x. Okay, e to the power xt. So e to the power xt is how much? This f xt is actually dt, right? This is actually the dt. So we have this one is equals to dt. Okay, so when you consider the ddt is actually, okay, forget these terms, huh? Forget this it. I think easier if I write down as x. Okay, so also forget all these things. So what we have here is d dt is equals to del f del x dxt, and this term, but this term when we have dxt multiplied, it will give us 0. So it's only del f del x dxt. What is del f del x? The del f del x is dt. Okay, this is dt. And what is dxt? Dxt is the minus rt dt. So we have minus rt dt dt. Clear? Clear? This one, the dt, this one dt is from our del f del x, and this is minus rt, and the dt is from our dxt. Okay, so we have ddt. Once we have ddt, very simple, is a d dt st is dt dst. The dst value is here. Okay, the dst value is here. So you write dt multiplied by dst. So dt multiplied by this term alpha t st dt plus sigma t st dwt. Okay. So you have a dt dst, and then the next term is st ddt. So st multiplied by minus rt dt dt. Clear? So you simplify and you will get this. Okay, you will get this. Okay. Until here, hopefully everything is very easy. Okay, until here. Sorry, until here. Uh, until here should be very easy. Okay, so once we have these, now you keep in mind, if you can write down in terms of dwt plus theta t dt, we can write that as dw tilde t, where w tilde is a new Brownian motion with respect to the risk neutral measure. So what we want to do here is we take common. So dtst is common, right? dtst here, this is dtst here is common. We need a dwt, so we also take the sigma t common. Okay, so we write sigma t dt st. So here we have only dwt. Okay, we only have dwt from the second term. From the first term we have alpha t minus rt divided by sigma t. Okay, so this term alpha t minus rt divided by sigma t dt. So this term we write as theta t. Okay, we write as theta t. Then we have theta t dt plus dwt. That means this whole thing, it's dw tilde t. Okay. So we have d dt st is equals to sigma t dt st dw tilde t. Okay. The next one is the portfolio process under the risk neutral measure. Okay, so it's same thing like I said last time. We initially we have this one, right? E to the power minus rtst and e to the power minus rtxt, and then we find the d of this and d of this. So we want to do the same thing, only the r is not fixed anymore, it's rt. Okay, the interest rate. Okay, so here first thing first, we have to write down what is dxt. Okay, maybe I write here how to write the dxt. dxt is the change in the portfolio. So first you have xt, this much money in your pocket, you spent delta t number of you bought delta t number of shares, and each of the share price st. So this much you spent delta t st, you had xt. So how much left? is xt minus delta t st. Now suppose there is a time change of dt, then how much will be the interest is rt multiplied by dt multiplied by whatever you have in the bank, okay, plus you already have delta t number of shares. Each of the share price was st. Now in terms of change in time dt, the change in value of the share is dst, suppose, okay. So then dxt will be this one, okay, this one. Clear? It's the same logic as we used in the binomial model, in the constant interest rate in continuous case, and also here. Okay, it's the same logic. So once we have it here, so what we do is we already know the DST. Okay, the DST value we already know. So we put the DST here. Okay, and then RTXT minus this one. So then we just simplify the thing. We have this. Okay, we have the thing here. Clear? So once we have this, okay, just a minute. So we have, okay, we have everything here. Okay, we have everything here. Okay, so once we have this one, then we have to find out d dt xt. Okay, d dt xt again simple, is dt dxt plus xt d dt. d dt we have found in the last page. We found d dt, and then the dxt is given by this. So you just simplify the thing, you will get this one. Okay, and then from this one we can also write this whole thing is actually is dw dwt. So we have this formula. Okay, so should be clear. So now we have just summarize the thing. So we have d dtst is sigma t dtst dw tilde t. So if you write down, so this one is the last result. So if you write in terms of integration, if you follow like integration 0 to t, so it's dtst minus d0 s0. Okay, so d0 is equals to 1, e to the power minus 0 is equals to 1. Okay, so you have dtst minus d0 s0 is integration 0 to t sigma u du su dw tilde u. Okay, from here integration, this one integration 0 to t. So this one is u. Okay, all these are u. Okay. So we have a formula of dtst. You see this one, if you write this whole thing as maybe as maybe delta u or something. Okay, so this is an adaptive stochastic process, and this is a Brownian motion w. So this whole thing is an Ito integration with respect to the p tilde, right? With respect to the p tilde, this whole thing is an Ito integration. Okay, if we have an Ito integration, that means this whole thing dtst is a martingale. Okay, so hence the discounted stock value is a martingale. Similarly, you can see that the discounted portfolio process is also a martingale. Okay, so you remember this one we have also done for last time. We have also done this in the binomial model. Okay, so once we have this, so since dtxt is a martingale, if you consider like you remember is a portfolio process is xt and payoffs are vt, then they must be equal. Okay, so you write dt vt because it is martingale. Dt vt is the martingale with respect to tilde. Okay, so we write e tilde. So dt vt is e tilde. This is the expiry time capital T. So it's e tilde dt vt given ft. Or maybe if you write d0 v0, that means it's v0 here. So d0 is 1. So if we have v0 is e tilde dt vt. Okay, this is the same formula we used in the binomial model. Okay, this is just a continuous case. Okay, so if you follow the Black-Scholes model, we can get this formula. The CTST is denoting the valuation, like the VT. So this one is actually is something similar to VT. CTST for call option. It will be E tilde. This is the DT minus T. So E to the power minus R T minus T. ST minus K plus. This is the VT, right? This is the VT. This is the DT and given FT. Okay. So that's all we have from the risk neutral measure. Um, Next, we discuss about forwards and futures in the next lecture. Okay, thank you.